Thanks, Hilton. It's great being here. I'm waiting for my presentation to show up. Yeah, there it is. So this is the title I chose for my talk, A Deep View on the Early Universe, Extreme Makeovers and Overweight Galaxies. And this first image you're seeing on this first slide is a view of the sky if you would be living on a planet when the universe was only 3 billion years old. And what you see is that this sky is filled with stars. And this is an artist's impression. It's obviously not a real picture. And I hope throughout this talk it will become clear why the sky will look like this. But let's first start with the galaxy that we know best, our own Milky Way. So here you see an image of our Milky Way. So the Milky Way has a couple of very characteristic features. It has this light concentration in the center. It's kind of reddish. It has this beautiful spiral arms around it. And our own Milky Way is this galaxy. So here you see it from face on. So we live somewhere in the outskirts of this galaxy, and we're actually rotating. So we're rotating with about 220 kilometers a second, or 140 miles a second. And our Milky Way is actually quite huge. So how big is it? Well, if you compare a football to the sun, that's how much bigger the Milky Way is compared to the sun. So it's really big, and it has hundreds of billions of stars in it. But our Milky Way is, so the picture as you see it here is actually not a picture how we can see it with our own eyes, because we live in this Milky Way. This is how we see it, and you already saw this picture before when you saw in the movie when they talked about the center of the Milky Way and the black hole that's there. And this is a nice view that we see of our Milky Way. But this is not a view you can see just with your eyes in one shot. This is the view you see if you would make a photo all over the Earth and throughout the year, so you can get an image of all pieces of the sky, and then you stick it all together, and this is the view that you get. And again, we're somewhere in the outskirts, and here's the center. So you see there's a lot of dark lanes here. That's actually dust that's obscuring our view. So our Milky Way turns out to be a pretty typical galaxy. For example, if we look at our nearest neighbor, the Andromeda Nebula, you see it actually looks pretty much alike. It's a kind of a different angle from which we see it, but they have a lot of things in common. For example, they have this concentration of light in the center. They have these bluish spiral arms at the outside. It's also this galaxy. It's also rotating. So why do we actually see these colors? Well, these colors tell us something about the stars that are living in these galaxies. So again, this galaxy is a little bit more massive than the Milky Way. It has, again, hundreds, if not thousands of billions of stars in them. And the reason why this is red is because the stars in the center are actually older than the stars in the disk. So blue colors means that we're looking at younger stars, and red colors means that we're looking at older stars. So the Milky Way and Andromeda actually look pretty much alike, but we also find other types of galaxies in the universe. Another type is, for example, M87, and that's the galaxy over here, and you immediately see the difference. This is what we call an elliptical galaxy. And the first striking difference is the color, right? It's red. And I already told you before, that's because it has older stars. So this has a very old stellar population. And it's roundish. There's no beautiful spiral arms. It looks kind of boring. And it's not a disk. It's actually 3D, so it's deep. And there are actually a lot of other differences as well between these elliptical galaxies on one hand and these spiral galaxies on the other hand. And one of the other differences is that elliptical galaxies actually contain many more stars. So if you would put that into a diagram, you can nicely divide it up into these two classes. Okay, so what am I showing here? On the x-axis, you see the mass in stars, and on the y-axis, you see the color or the age. So this is young, this is old, this is light, and this is heavy. And most of the galaxies fall in one of these two classes. You're or a spiral or you're an elliptical, pretty much. So the spiral galaxies live over here. They're pretty light. They have a lot of stars, but not as much compared to the elliptical galaxies. They're bluish, it means they're younger, so they're basically young and light. While these elliptical galaxies over here, they're older and they're heavy. So one thing that astronomers want to understand is where do these two classes come from and how are they related to each other? And in order to simplify things, we have two very simple names for these two groups. We call this the blue cloud, and we call that the red sequence, because they actually sort of span nice sequences or clouds in this age mass space. So galaxies do not live in the same spot throughout time. They actually move around. They change in age and they change in mass. So how can they change? Well, first, if you're a galaxy that's blue, you're forming stars. If you're forming stars, you get more mass in stars. So you can basically move in this direction by forming new stars. So a galaxy can be here, and then a couple of billion years later, it can be over here. So what else can happen? Well, these galaxies over here, the red sequence galaxies, these red elliptical galaxies, they have a lot of stars. These stars must have formed at some point in time. So we know that all the galaxies that live here at some point must have been here. So we know that there are transformations. But then, once a galaxy is an elliptical galaxy, does it just stay there? Well, actually not. It can still change too, and that is by meeting a neighbor and colliding and then merging together and becoming a bigger galaxy. That's what we call mergers. And galaxies can move along this red sequence by mergers. So here you see the basic physical ways how galaxies grow over time, and how that changes on one hand how big they are, how many stars they have, and on the other hand, their age. So one of the key questions for us is try to understand the connection, how does this happen, and how do these galaxies grow? And we can do that by just looking at these beautiful pictures that I showed you before and analyzing that. But we astronomers are pretty lucky, and we actually have a much better way of doing that, which is much more direct, and that is by actually looking back in time. Because the light has a finite speed, which means that we can see objects in galaxies much further in time. So, for example, our sun, we don't see the sun at this moment. Well, at this moment we don't see any sun, but when it's during the day, the light that we receive, that actually traveled 8 minutes. So that means that we see the sun how it was 8 minutes ago. The closest star is 4 light years away, which means that we see that star how it was 4 years ago. Same for Andromeda. We don't see Andromeda at this moment. We see Andromeda how it looked like 2.4 million years ago. And we can look as far back as to the afterglow of the Big Bang. We can look as far back as 13.7 billion years in time, when the universe was still very smooth. So this means for us, people who study galaxies, that we can see galaxies throughout the history of the universe. So here you see a nice illustration of the history of the universe up to all the way back to the Big Bang. And we can see galaxies over about this time. So we can see galaxies at 1 billion years old when the universe was 2 billion years old, all the way to now. But you can only see a galaxy at one point. So you cannot track one galaxy over time. Each galaxy you only see at one point in time. The farther the galaxy is, the longer it took for the light to come to us, which means that we see the universe at an older point. Okay, so this seems easy, right? Why don't we just observe galaxies throughout cosmic time, and then we can see how they evolve? Well, it's not as easy as it sounds, because galaxies get fainter if you look further back in time. So if you really want to understand how the most distant galaxies look like, you have to look at one piece in the sky for a very, very long time and collect light for a very, very long time. So you cannot do that with the whole sky. So astronomers have picked a particular piece in the sky, or actually a couple, in which they put their telescopes and pointed for hours, days, weeks at the same time and collected all the light in order to make a very deep photo. So here you can see a movie illustrating at what piece of the sky they're looking and how tiny that piece actually is. So here you see some constellations. We're zooming in. We're zooming further in. This is what's called the Hubble Ultra Deep Field. It's done by the Hubble Space Telescope. So you see how far we're zooming in. And there, finally, there's a piece that they actually observed for weeks at a time. All these things you see here, we're now doing a fly-through. these are all galaxies, except for 2 objects which are stars, but the other ones are all galaxies at different points in time. So the light has traveled different times to reach us. And we're gonna end up with this red little dot here. That's actually the furthest galaxy so far being identified. Okay. So, distant galaxies are faint. That makes it hard, but that's not the only thing that makes it hard. Another thing that makes it complicated is that the universe is expanding. And likely you've already heard about this, but you can compare this with this famous balloon kind of analogy, in which you put coins in a balloon, you blow them up, and you see that the coins move farther away from each other, but the coins stay by themselves. So basically, here you see this balloon with galaxies put on top of it. The galaxies stay the same size because they're bound by their own gravity, but they move farther away from each other. So why is this important for us? Well, the problem is that because the universe is expanding, these very distant galaxies, they're moving away from us. And they're moving with such long speeds that the light that's traveling towards us has also been expanded along with the universe. So that's one way of looking at it. The other way of looking at it is this is actually a very big Doppler shift. So the light has been redshifted because the galaxies are moving away from us. Okay, so what am I talking about? Well, what you see here, and this may be a little complicated, but what you see here is a brightness distribution of a galaxy. And this is particular an elliptical galaxy, a red galaxy. So here's brightness, here's the wavelength. This is how the brightness distribution looks like, and this is what our eyes are sensitive to. So this is the visible light. All the way from the UV over here to the very red part over here. And this galaxy is pretty nearby. It's actually basically maybe our neighbor or such. But what happens if this galaxy would shift and would be farther away? Well, this is what's happening. So the galaxy is shifting to farther distances, and you see it's moving out of our visible regime. We cannot observe it anymore once it's like 7 billion light years away. And here it's like 9 billion light years away. And so basically what's happening here is that light that is emitted at optical wavelengths, so emitted at visible wavelengths, the light that we can see, by the time it reaches our Earth, it's not visible anymore. It's infrared light, or specifically near-infrared light, which is heat radiation. So as we'll see later on, fortunately, the Keck telescope is not only sensitive to the visible, but also to the near-infrared. Okay, but let's go back to these distant galaxies. So you see that if you really want to study these elliptical galaxies in a very early universe, you need an infrared telescope. You cannot do it with a visible telescope. So fortunately, Hubble has infrared capabilities as well. So we took some really nice images of galaxies in the very early universe with Hubble, and you can see it over here. And we concluded, hey, elliptical galaxies already existed when the universe was still very, very young, as you can see over here. And these don't look as nice as these images that I've showed you before because these things are very faint, but you can kind of see that they're pretty similar in the fact that they are pretty regular. They don't look like disks, and we also know that they actually have older stars, so they're actually red. But one thing that we found, which was really striking, is that these galaxies are actually much smaller compared to elliptical galaxies nowadays. And with smaller, I don't mean they have less stars. No, I mean that they actually pack much more stars in a much smaller space than they do today. So they're much more compact, they're much more dense. So just to show you a comparison with our Milky Way, imagine you put all those stars here in the Milky Way in this tiny galaxy. That's how compact they are. And that's how dense they are. So what happens then if you live in such a galaxy, in such an ultra-compact galaxy? Well, this is how your sky looks like. So that's explaining that sky that's completely filled with stars, where it almost doesn't get dark, because there's so many stars packed in such a small galaxy. So this discovery was done like about 5 years ago, maybe a little longer, and this puzzled a lot of astronomers, and they were like, what's going on here? This cannot be true. How can these elliptical galaxies be so much smaller at early times? Because these are elliptical galaxies. They're red, which means they have old stars, which means they're not forming any new stars anymore. How can they grow over time? What's happening there? So this is basically the picture. So this is the early universe, about 3 billion years after the Big Bang. You have these tiny little compact things, and then they get bigger and bigger over time, and then nowadays they're very fuzzy. How can they puff up? What's going on here? Okay, so that's the first question I would like to address. So how do these distant elliptical galaxies grow in size without forming new stars? What's going on there? So there's a couple of theories out there, and I'm going to show you a couple which we think may be plausible, but there's definitely not a firm conclusion yet on this topic. Okay, this is kind of a little bit cut off, but here it says growth by transforming blue larger galaxies. Okay, what do I mean there? Imagine I have a group of galaxies. I have blue galaxies and I have red galaxies. I know the bluer galaxies are a bit bigger than the red galaxies. Here you see this group. Let's now go a couple of steps forward in time, and let's think that, for example, a couple of these blue galaxies will stop forming any new stars and will become red. And then it will look something like this. Okay, so if I now count these galaxies and I count the size, then I see that the average size of red galaxies is smaller here than it is here. So one plausible explanation for the size growth is that you just make redder galaxies at later times out of blue galaxies, and these ones are just bigger, and then you get an average size which is bigger, right? So the average size of red galaxies becomes larger. Okay, let's keep this in mind, and let's see which ones are the new additions, which ones are the ones that become red later on. That's this one, and that's this one. If this theory is true, then you can see that the older red galaxies are smaller than the newer red galaxies, than the younger red galaxies. So I give them a Y for the word young. Okay, let's test that. Is that true? Well, if you then look at the brightness distribution, so basically the size, and here you see the images of a young quiescent galaxy or young elliptical galaxy and an old elliptical galaxy, and here you see basically cut through the center all the way down, you find they have pretty much the same size. If not, the younger one is actually a little smaller. Okay, so that means this theory doesn't work. We need another theory. So another thing that we have to keep in mind is that our universe is actually not static. I already told you that it's expanding, but something else that's happening is that structure is growing over time. And it's collapsing on itself over time. It's clumping together, which you can really nicely see in this illustration, in which this is a very early time in the universe, and you see that matter is distributed pretty flat. And this is about, like, I think 3 billion years after the Big Bang. You see that the matter is a little bit more clustered together. And this is nowadays, and the matter is much more clustered together. So you see it's falling in. Okay, this looks, here you see the box for a very big part of the universe, but how does this look like if you actually look at individual galaxies? So here you see a computer simulation going all the way back to very early in the universe, and then you see how matter is collapsing on top of each other and growing into bigger structures and bigger objects over time. So you start off very smooth, and you see all these different blobs are all galaxies, and they're all falling on top of each other. There's little things falling in all the time, big things that are merging together, and things get more clumped going through time. Hey, can we use this? Is this maybe contributing to what we're seeing? And is this actually true? Do we really see this in the universe? Because this is a simulation. This is not the real universe. We cannot see this in the real universe. But if we really go take very deep images, very deep photos of elliptical galaxies around us, we actually see that a lot of them show some signatures of merging activity, of collisions. As you can see over here, there are some features here. Here you actually see two galaxies colliding. This is also a feature that indicates that maybe something merged into there. So what if these galaxies are not growing by forming new stars, but they're actually growing by eating up small galaxies around them, by merging with smaller galaxies? Would that be possible? Well, if you actually look at how the density, the mass density, is divided in a galaxy, this actually seems pretty plausible. Okay, so this figure I'm showing here is the mass density profile versus the radius. So this is the center, this is the outskirts, and this is a distant elliptical galaxy, and this is a today's elliptical galaxy. And what you're seeing here, the center is pretty similar. There's not that much difference. The difference is really at the outskirts. So you see a large difference over here. So this really tells us that these galaxies grow inside out, likely by accreting smaller galaxies around them. So if we go back to this picture, so what does this mean? Well, this means that this galaxy over here is actually the core of the galaxy over here. And all this material that you see here is not originally from this galaxy. It's formed in another galaxy, and it's accreted, it's merged later on, and it's absorbed by this bigger galaxy, and that's what's forming these wings. So this is the most popular theory. We're actually not really sure whether this is the right theory, but this is definitely the most popular theory today. But I'll come back to this later. So another question that I sort of alluded to in the beginning is, but what is actually the connection between these spirals and ellipticals? I told you these spirals will probably not stay spirals always, and these ellipticals must have formed stars at some point, right? So the thing to do now is to also look at galaxies that are forming stars in the early universe and see what we can learn from that. So these spiral galaxies, do we find them when the universe was still very young? Well, we actually do, but also these galaxies don't really look the same as the ones today. And here you see a couple of photos of spiral galaxies or star-forming galaxies, blue galaxies, when the universe was still very young, also about 3 billion years. And what you see here is you can sort of see kind of a disky shape, and maybe there's some spiral arms, but they're actually pretty irregular and they're pretty clumpy. They have all these clumps in them. But the big question is this: how do we go from something that looks like this to something that looks like that? Because these clumpy star-forming disk galaxies are actually much bigger than these compact elliptical galaxies. So how do we do that? Well, this is another big question that I'm not going to give you the final answer to, because there are several theories out there, and there are several people who think they know the right answer, but I don't think we really have a firm conclusion here yet. Okay, what's one of the theories? One of the theories is that all these different clumps that you see here eventually fall to the center, they migrate to the center, they merge together, and then they form something that you see over here. So in order for people to show that this is true, they try to simulate it on their computers. They start with the galaxies like this, and they simulate it forward in time, and they see how it would look like. And here you see a couple of those simulations. So time goes into the horizontal direction, and here you see 3 different simulations. So you start off with something like this, and you see those clumps are migrating to the center, and you end up with something that maybe looks like a compact galaxy. Seems maybe like a plausible theory. But what else? What else could do it? Well, another very popular theory is that these disk galaxies are actually merging together in order to form one of those compact galaxies. Okay, so what am I talking about? Well, here you can see in a simulation how that would look like. So you have 2 disk galaxies. They're colliding, they're meeting each other. You see there's a first encounter, there's going to be a second encounter, and eventually they will merge together to something pretty compact. So this seems a very plausible theory as well, but it's actually not really proven that this is really the way to make very compact elliptical galaxies. But one thing that we do know is that mergers like this exist in the universe. We do know they exist. We don't really know whether this is the way to make compact elliptical galaxies. So one of the ways how we know that mergers exist is just by looking at these beautiful images that we take of all those galaxies, which you can see over here. So you see like galaxies ordered into like different phases of a merger. So here they're just nearby, they're neighbors. Here they get closer to each other and you see some interaction. Here they're really close. And this is one of the more final merger products that you could get. Okay, so lots of questions, lots of theories. We need to go forward, so how are we gonna do that? So lots of the work I've showed you so far is based on the Hubble Space Telescope. And in particular, beautiful images, very deep photos from the Hubble Space Telescope. But if you really want to learn what's going on and you really want to learn the physics, you should not use photos, you should actually use spectroscopy. So you should analyze the light and disperse it, and then you can learn a lot what the physics really is that's going on in these galaxies. So this is not something that's possible with the Hubble Space Telescope, and that's exactly where Keck comes in. So very recently, Keck got this new instrument, and this instrument is called MOSFIRE. It's a multi-object near-infrared spectrograph. Okay, so this is a lot of terms in one little sentence, so what am I talking about? Multi-object, that means that you can actually observe several galaxies at the same time. And here I'm in particular talking about very distant galaxies. Near-infrared, okay, I talked to you about that term before. That means more like heat radiation, and it in particular means that we can observe the optical light from galaxies in the very early universe, or the visible light. So the light that we see with our eyes, by the time it reaches us, it will be infrared light. So this instrument is particularly suitable to study very distant galaxies. And then spectrograph. And spectrograph means that we're really dispersing the light, and we're looking at the brightness as a function of the wavelength, like in a rainbow. Okay, so using this instrument, we started this new program. It's called the MOSFIRE Deep Evolution Field Survey. And we did this with a group of people at the University of California. And the idea is to obtain spectra, so to obtain spectroscopy of 2,000 galaxies when the universe was 1.5 to 4.5 billion years old. Okay, so what am I talking about when I'm talking about spectra? So how does this actually look like? So I want to give you kind of an illustration of like how this data and how these photos or these spectra look, like how they look like and what we do with them before we can actually use them. So here again you see a really nice photo of the Hubble Space Telescope. This is a very long exposure again. This is observed for hours and hours, maybe even days. But we're interested in analyzing a couple of the galaxies that you're seeing here in much detail. So lots of the galaxies, almost everything you see here is a galaxy. All these little blobs are all galaxies at different points in time. You see a star here, and I think there's another star there, but the rest are all galaxies. And we're particularly interested in things that are about 1.5 to 4.5 billion years after the Big Bang. Okay, so how do we do that? Well, with MOSFIRE, you can put slits on top of the galaxies. So here you see kind of the slit. So basically you're masking out all the other light and you make tiny little slits through which you observe the light. So the next thing you do is behind these slits, you put a disperser, like a prism, in order to disperse the light as a function of wavelength. Okay, let's now look at this particular galaxy somewhere on top. It's a little high, but you can sort of see it. It's like this little galaxy over here. And let's now get the MOSFIRE data. Let's now get MOSFIRE to work. So we block all the other light. We only look at the light that goes through these yellow little slits. We put a prism behind it, and this is what you get. So you see there's lots of stuff going on. There's a lot of different lines over here. So if you go up in this direction, you're still looking in the spatial direction, as here. So you still go up, this is still the spatial direction. But if you now go in the horizontal direction, it's not spatial anymore, it's actually wavelength. So each of these lines are at a different wavelength. Okay, let's now look at this one in particular, and it's kind of unfortunate, it's so high up, but there's actually not that much to see. You see all those lines. So what are those lines? Well, these are not the galaxy that I'm interested in. These lines, that's atmosphere. That's all atmosphere that we want to get rid of. Okay, so let's try to get rid of the atmosphere. Let's remove it. And what you see then is this. And this is actually a galaxy spectrum. This is the spectrum of a galaxy when the universe was only 3 billion years old. So you go basically from this, you remove all those lines, these bright sky lines, which are all polluting, which are like making our analysis very difficult. We remove those, and this is what you have left. So you see, on one hand, you see some white blobs and you see some dark blobs. The dark blobs are just a negative of the white one, and these are a byproduct of how we analyze our data. So let's ignore the black ones. Let's just look at the white ones. So what are these things I'm looking at? What is this? Well, this is actually hydrogen, and this is actually oxygen from a galaxy in a very distant universe. So this light traveled 11 billion years to reach us. And this is not just a galaxy light. No, this is particular hydrogen and oxygen. Okay, let's look at another galaxy. Let's look at the one down there, which is also, unfortunately, a little cut off, but it's the one over here. It's actually a little bit brighter than the galaxy over there. Okay, so again, we do the same thing. We put this prism behind it, we disperse the light into different wavelengths, and then we get rid of everything behind just to zoom in on this one because we're interested in this particular galaxy. We remove all those ugly, bright, vertical features, which is the atmosphere. So remove the atmosphere, and this is what you have left. Again, this is the positive signal, and these are the two negative ones, which we're just going to ignore for now. Okay, what are we looking at here? So the difference is, here you actually see kind of blobs. Here you see just a continuum, a continuous signal all the way through. So this is actually the stellar light of a very distant galaxy. Again, when the universe was about like 3 billion years old. 3 billion years old. So this light has also traveled 11 billion years to reach us. Okay, well, this is great, but what can we learn from this? What can we do with this? Well, we can actually learn a lot from it. So this is what we call an emission line, and this is what we call continuum emission. And in this continuum emission, there's actually lots of little absorption lines, which I will come back in a second. But let's first look at these emission lines. Okay. So this is, again, this emission line, and let's now collapse it. So this is 2D. Let's now collapse it. This is like spatial direction. This is wavelength direction along this spatial direction. And let's then make a 1D spectrum. So this is the emission line. This is the brightness. This is the wavelength. So what are we actually looking at? I was telling you before, we're looking at oxygen and hydrogen. So what can we learn from this? Well, this is actually, these lines come from interstellar gas heated by hot stars. So this is the gas in between the stars in these very distant galaxies. So the very hot stars are heating this gas, and that heated gas is causing this line. And that is great, because that is telling us a lot about what's going on in this very distant galaxy. We can, for example, learn about what is this galaxy composed of, in particular, what is the gas composed of. We can learn about the temperature of this gas, and we can learn about how many stars are actually being formed in this galaxy, because you need these hot stars to actually heat the gas. So from that, we can derive what the stellar birth rate is. Okay. I also told you there's absorption lines. So we had this more like kind of continuous light over here. And in this continuum light, there's like sort of dips in the brightness. You can sort of see them over here. They're little dips. And if you would collapse this again along this spatial direction, you would get something that looks like this. So you get this absorption line. So the nice thing here is that this light all comes from stars. And these absorption features actually come from stellar atmospheres. And again, that is also telling us a lot about what's happening in these very distant galaxies. So now we can not only know about the composition of the gas, we can also learn about the composition of stars. We can learn about the temperature of the stars, and the temperature tells us again what the age is of the stars, and we can learn about when the stars were actually formed, so we can learn something about the star formation history. So you see, from these MOSFIRE spectra, we suddenly can learn so much more than just taking a photo, a very deep photo of the sky. We can really learn what's going on in these very, very distant galaxies. And you may wonder, okay, but why is this important, and how does that couple back to the story that you told us before about these, for example, these elliptical galaxies growing in size? Okay, so let's go back to elliptical galaxies and their size growth. So this is a diagram on the left that I sort of showed you before. And in the beginning, in one of the first slides, I put little images of galaxies on there. So here, on the y-axis, you see the age, and on the x-axis, you see mass. And this is where today's elliptical galaxies sort of fall. These are the elliptical, this is the red sequence. I call this the red sequence. So you see that the more massive galaxies are slightly older than the less massive galaxies. That's basically what the red sequence is telling us, because you see there's a slope in this, there's a trend here that's going up. So the more massive galaxies are older. But this is not the only trend that we see in elliptical galaxies. What we also see is that elliptical galaxies that are more massive also have heavier elements. So what do astronomers mean with heavier elements? Well, we mean anything that's heavier than helium and hydrogen. These are all elements that have been made in stars. And you see that the more massive galaxies actually have a higher amount of heavy elements than the lower mass galaxies. So this is today, these white lines, and I want to give you an idea of how this may look like in the early times for different scenarios. So imagine that elliptical galaxies, as some people say, are actually not merging over time. They're not merging with any other galaxies. So no mergers. How would this trend look like at early times? Well, elliptical galaxies would be younger. So this line will go down. There's no mergers, and there's also no star formation, because elliptical galaxies are red. They don't make any stars anymore, so the mass doesn't change. So in a distant universe, this relation would be somewhere here. Okay, how would this one look like? Well, heavy elements. If there's no mergers and the galaxy is just aging, the heavy elements will stay the same, because the only way to change the heavy elements is if you actually make new stars. Okay, so this is how this relation would look like in a distant universe. However, if we actually live in a universe in which these elliptical galaxies do merge, these relations, these trends would actually look very different in a distant universe. They would look like this. Okay, let's flip that back. There. So this one is a little bit shifted, because galaxies don't only get older over time, they also get more massive. And what's going on here is that you see that actually the amount of heavy elements is going down. Why is that? Well, imagine you're a very massive elliptical galaxy, and then you merge with galaxies that are also elliptical, but they're less massive. So you live here, you merge with something that's here, you basically merge with something, or you collide with something that has a lower number of heavy elements. So if you have something that has a lot of heavy elements, and then you mix it with something with less heavy elements, then the final product will also have less heavy elements. So this is basically telling you that we expect, in this merger scenario, that galaxies in the very early universe have much higher relative heavy elements abundance than it does have in the local universe. So, and this is something we can really learn from MOSFIRE. Okay, so what else can we learn from this great spectra? So we had emission lines over here, and we had absorption lines over here. And we can actually learn something about how stars are moving in these galaxies. We can actually learn something about the stellar motions. On one hand, we can also learn about the gas motions. Okay, so what am I talking about? Well, let's ignore the gas for now. Let's look at this one. So this line is a stellar atmosphere line. It's made in the stellar atmosphere. But it's not only made in the stellar atmosphere of one star. No, it's the accumulation of the atmospheres of all those different stars, all put together. Now imagine that these stars are moving around with a certain speed, with a certain velocity. Then this line will not always be at exactly the same spot, because all these galaxies with a different velocity will have a slight Doppler shift. So stars that are moving slightly away within the galaxy, they will be a little redshifted. Stars that are moving relatively towards us within this galaxy will be a little bit blue shifted. So what does this mean? Well, if this is, for example, the line width for stars that are moving with about this speeds, and now you increase these speeds, you make this line broader. So basically, from the width of this absorption line, you can learn by what speeds these stars are moving within the galaxy. For a galaxy that is 11 billion years away, you can even do that for the gas. You can learn how the gas is moving, what kind of speed the gas is moving. And why is this important? Well, the speed of the stars tells us something about how massive these galaxies actually really are, because this is a direct probe of what the gravity in this system really is. Okay, so you've been telling you a lot about what we can do with these wonderful spectra, and the reason why I don't have a lot of new results yet is because this survey actually just recently started, the MOSFIRE Deep Evolution Field Survey. We actually had our first publication out today, and we're 1.5 in total, about 2,000 galaxies. So at this moment, we're at about 600. So we're not there yet, and this will be an ongoing project. So there will be lots of interesting results coming out in the coming years, and I hope to have a lot of answers to the questions I proposed today, and that's where I want to end this talk. Thanks.